Hey, good day all. Yeah, welcome to another video of mine. Today we're going to be looking at eigenvalues and eigenvectors. This topic is just one I would like to rush through. Now, for us to understand the reason for some things in eigenvectors and eigenvalue, we have to define those four terms. Now, the first one is what you call um, being a function being what? Homogeneous. Homogeneous. And a matrix being homogeneous. So I can say homogeneous matrix. Okay. Now, when a system, okay, I'm gonna say, yeah, homogeneous. Okay, so when a system, let's say A of X is equal, this is a matrix. This is a matrix. So A is a matrix and is a square matrix. What I would like to say before I go further is that eigenvalues and eigenvectors are square matrix terminology. You don't use them for matrices that are not square, something like 0, 1, like something like this. It doesn't go for matrices that are not what? Square. When I mean by square, that means each rule and each column will have the same number of values. So we can represent it as n times what? N. So eigenvalues and eigenvectors are actually square matrix terminology. They're not associated with any other form of matrix. So let's say this our A here is a square matrix. Our X here is not a square matrix, and it's actually representing the variables of an equation or of a system, and your B here representing the constants. Now, for we to say that this system or this, I would like to call it this to be system and not matrix. This is actually okay. Homogeneous word system. Now, for this system to be called homogeneous, our B should be a zero matrix. When I say zero matrix, it means that all its component of this matrix are what? Zeros. You don't see any other number in it, just what? Zero. So when our B is a zero matrix, the system is said to be what? Homogeneous. Another one is the inhomogeneous. Now a system like that is inhomogeneous, system like this, our B is not equal to what? It's not a zero matrix. Like I said, zero matrix is like not like this 0 0. So long it all its elements or all its components are zero, that would we call a zero matrix. So when B is not a zero matrix, it is called this system is called what? Inhomogeneous system. Now the third term we're going to be looking at is what you call singular matrix. That was the one I was trying to explain at first, and I was kind of intertwining the two of them. So our singular matrix is a matrix. Let's say matrix A, which is a square matrix. So let's say of dimension n of n, meaning that it's a square matrix, if the determinant of A gives us 0, it is called a singular matrix. Now, the next one and the last is what we call the non-singular matrix. When the determinant of our A is not equal to 0, it is called a what? A non-singular matrix. Now, these four terminologies have, just let me say, this is your homogeneous. A system can be homogeneous or inhomogeneous. There's four possibilities of combination. These two can't be in the same system. A system cannot be homogeneous at the same time be inhomogeneous. Neither can a matrix be singular at the same time be non-singular. So it's either this. For the next one, we are having this is a system. That is a system, and for the matrix part, now when these two go together, when these two go together, when they go together, the solution of our x, let me write it somewhere around here. So when H for homogeneous and non-singular goes together, our x in this case, this matrix is a 0 matrix. When your homogeneous goes with your singular, you have an infinite number of solutions for your x. So your x is going to be having an infinite number of solutions. Now, when your inhomogeneous goes with your singular, you are going to have no solution. And the last but not the least, when your inhomogeneous goes with your non-homogeneous, then your x is going to be using this system expressed in the inverse of A times B. So this is inhomogeneous and non-singular, homogeneous non-singular, homogeneous singular, inhomogeneous singular. So these are the conditions. When these two, when they combine, they have four possible combinations, and in each of them, they will give you this particular solution. So the reason for this is that you can be given a matrix, and you are asked, and maybe your matrix is actually inhomogeneous, and at the same time singular, and they ask you to find the value of your x. You can spend your time, or maybe you can even get confused in the exam hall, not knowing that matrix actually has no solution. So you can't actually get the value of x in such system. A system that is singular at the same time, a matrix that is singular in a inhomogeneous system. You can't get a value of x in such this thing. So the reason why this was brought up was because of our eigenvalue actually follows this one, which is that of your homogeneous in a singular matrix. So an eigenvalue has a way its problem is being expressed in. For us to express an eigenvalue, this is the formula we use. Where A is a square matrix, X is representing the variables which are in a single column but as many as rows instead of your A, and it's all equal to your lambda, which is a scalar, multiplied by your X. Okay, so like we said earlier, the eigenvalue has infinite number of solution. So what this means is that taking every single one with variable to the left hand side, we can write this to be ax minus lambda x is equal to what? 0. As you can see from this equation, the one without a variable, which is our constant, is what? 0. So this is a what? A homogeneous system. This is a homogeneous system. You can also go further to factor out our x, and we have, and remember that your lambda is a scalar. So to make it a in a matrix form, or to make it a vector having rows and column, we are going to be multiplying by the identity matrix. When we do that, we have that our a minus lambda all multiplied by our x is equal to what? 0. So this tells us that our eigenvector is what? A homogeneous system. It's a homogeneous system. Remember, this is identity matrix. Identity matrix for 2 by 2 is totally a diagonal matrix. What you have is in your major column, what you have there is just 1, and the other in the major diagonal, what you have there is just 1, and the rest is just 0. This is for your 2 by 2. For your 3 by 3, what you have is your 1 1 1 0 0 0 0 0 0. This is for your 3 by 3. This your identity matrix is constant. It doesn't change. Your diagonal will have 1. The other elements of the matrix will have what? 0. That's what this your I here represents. And we introduced it here because of what our lambda is a scalar. It doesn't have row and column. So we want to subtract this from this, and we can't do that without making this our scalar a vector, which is just by multiplying it by our what? Identity matrix. Now, like we said earlier, let's not go too far. We have shown that an eigenvalue problem is actually a homogeneous system. Now, we say that the thing will also be having an infinite number of solutions, meaning that the other requirement left to be satisfied is that of the singular matrix. So remember when we say that if you have a system where you have your Ax is equal to b, if the determinant of your A is equal to 0, we call it what? Singular. Now, in this case, our B is 0. Our A is representing the whole of this one in brackets, which is your A minus lambda I. Your X is to your X. So, what this means is that the determinants of your A minus lambda I is equal to what? 0. This two satisfies the requirement for your x having an infinite number of what? Solution. And this one is telling us that our a minus this thing minus lambda this thing is the what? Singular matrix. Okay, now what we call this is what? The characteristics what? Equation. So when you are given an eigenvalue and eigenvector problem to solve, we use the characteristics equation to find our eigenvalue and use this one, this eigenvalue problem to get your eigenvector. So with that out of the way, let's try an example. Remember, the two formula we need to know is that your ax is equal to lambda x, and your eigen problem equation, and that the determinant of your a minus lambda I is equal to what? 0. So given this matrix to solve, okay, so find the eigenvalues and eigenvector of a matrix where your of matrix A is equal to 3, 2, 2, 3. And this is a 2 by 2 matrix. And remember, your A must be a square matrix. If it is not a square matrix, you can't find the eigenvalue and eigenvector. Okay, now with that out of the way, let us get our eigenvalue using this characteristics equation. Now, using this, we're going to be having that the determinants of 3, 2, 2, 3 minus lambda multiplying our identity matrix. The identity matrix is now going to be a 2 by 2 because our A is the what? 2 by 2. We're going to be having 1, 0, 0, 1. Also, now the graph stuff is quite easy. Okay, now when we multiply, we're going to be having this down here 3, 2, 2, 3 minus your lambda. When we multiply your lambda now, for every single thing here, what to multiply is just lambda, not minus lambda. When we do that, we have lambda 0, 0, lambda. So like we are saying, our aim is to make lambda a what? A matrix. So we can subtract. So in doing that is equal to what? 0. Now we can now go further to simplify. From here, 3 minus, we'll be having a matrix of what? 3 minus lambda is still 3 minus lambda. 2 minus 0 is 2. And 2 minus 0 is still 2. And 3 minus lambda is still 3 minus what? Lambda. Okay. Now, this will give us still what? 0. Now, the determinant of this will be 3 minus 3 minus lambda. Then minus the major diagonal minus the what? Minor diagonal. We have multiplied these two, which is this. Now, the multiple of these two is 4. Minus the minor diagonal is equal to what? 0. Opening the bracket here, will be having 9 minus 6 lambda and plus lambda what? Square minus 4 is equal to what? 0. 9 minus 4, we have 5. So we can write this to be lambda square minus 6 lambda plus what? 5 is equal to what? 0. Now, using your quadratic equation or calculator, you can get what your lambda is. I'll be making use of the calculator. I hope we know how to make use of a calculator. You click on your mode and you will see from 1 to 8 options. You click on 5. Then since this is a quadratic equation is number 3. You click on 3. then you see a box popping up. What you'll be typing in now is now the coefficient of each of this one. I mean, that is when you have arranged the thing in form of square, the power of 2, power of 1, and then power of 0. Like this lambda is raised power 2, raised power 1. There is no 1 here. So it has to be in this arrangement for you to make use of the calculator. So imputing the coefficient, the number in front of it, you have 1, and you click equal to, this is for the A part. Click equal to your B part, you have minus 6. You click equal to, minus 6 is the coefficient of this one. Click equal to, and then 5. And we have that our lambda, I will say lambda 1 is equal to what? 5. And our lambda 2 is equal to what? Is equal to 1. So we have gotten our eigenvalues. Our first eigenvalue is what? 1. And our second eigenvalue is what? 2. Now, eigenvalues will kind of are used to get your eigenvectors. So we have gotten our lambda using this formula. We now have to go back to this formula to get our corresponding x value. Our corresponding x value there are our distance, our eigenvector. They represent our eigenvector. So our eigenvector, unlike our lambda, is our lambda here is a scalar. 5 and 1 is a scalar, not a matrix. But our eigenvector, on the other hand, is a matrix. And it has the form of row by column. That is, let's say n times 1. If this is a 2 by 2, that will be the matrix of your eigenvector will be 2 times 1. That is what? 2 rows, but what? 1 column. So going back to this formula, this first one, we're going to be having this. Remember what your A is. This is your A. So you're having 3, 2, 2, 3 in matrix multiply. Our x is representing the variable, so I can call it x and y, and this is equal to the lambda. Now the lambda, now we have 2, so each of them are going to be giving us each of their own corresponding what? Eigenvector. So this one will have its own separate eigenvector, this one will have its own separate eigenvector, and our x, y. Now in some textbooks they might not use y, but they will prefer to use x1 subscript 1 and x subscript 2, just to signify the that this is the first one, this is the second x, the first x and second x, but I prefer to use x and y to make it a much more distinct. Now finding for the eigenvector for the first eigenvalue. So when our eigenvalue is equal to what? 5, we're going to be having 3, 2, 3, 5 x, y is equal to 5 times your x, y. Now substituting our like multiplying this stuff, we're going to be having 3. What's happening here now? Okay, 2, 3. Okay, so 2, 2, 3. This will give us 5x and 5y. Then we can go further. We have, now we're going to now multiply for this one. I'm going to be we're getting our normal equation form. I'm going to I'm removing it from its matrix form and taking it back to its normal equation form. So doing that, we're going to be multiplying. We're going to be multiplying. When we multiply, we do this times this plus this times this. That will be on that one. Then everything will equal to this 5x. So when we do that, we have 3 times x plus 2 times y is equal to what? 5x. And for the next one, which is this, we're going to be having 2x, 2 times x. See how we do this? The row multiply the column. The row multiply the column, and you add the two of them together. Now this second row now, 2 times x is 2x plus 3 times y, 3y, and all this is equal to what? 5y. Now from here we can go further to simplify, and we have that our taking our 5, okay, bringing our 3 over here, we have 2y is equal to, when your 3 comes over here, it's going to become minus. So 5 minus 3, we're going to be having 2x. So we can also go further to say that your y is equal to your what? X. When you divide both sides by 2, you have this. So another thing I'd like to say is that our aim in eigenvector is not to get a number. We are not going to be getting numbers, but actually variables. So we are trying to find a way to express the two variables that we have in terms of each other. So now we'll be able to express y in terms of what? X. Now let us solve for this one. Here we're going to be having that 2x is equal to, when this guy comes over here, it's now going to become what? 2y. This is 5. When this crosses, it becomes plus 5 minus 3y. We're having what? 2y. This is also telling us what? The same thing. That what? X is equal to what? Is equal to what? Y. Now you then go back to this your eigenvector representation here. They then say that your x1, which is the first eigenvector for your first eigenvalue, is equal to, this is supposed to be equal to your x and y as written here. But from what we have gotten, we are seeing that both x and y are what? The same. This is telling us that y is equal to x, and this is telling us that x is equal to y. So they are the same. So we can actually rewrite this to be what? X and what? X. As if we have to substitute for this guy, we can write this as this. Now this is our what? Our eigenvector. We're not going to be leaving it like this. So we're not going to assume that our x is now a number. The aim first of all is to get a variable. Then you then after getting the it in variable form, you then assume a number to it. It can be 2, 3, 4, 5, 6, 7, 8. But we normally do select 1. I guess it's to make the work a bit easier. So when you do that, you're going to be having that this is also similar to what? 1, 1. So what this means is that if your x is 1, your y will be 1. And you'll be having your first vector to be this. Now another thing again that they might also tell you to do, or that is always required for of you to do, is to normalize the vector. When you're done solving for your x1 and you get to this point, you don't actually stop here. You normalize the vector. Normalizing of vector, let us say that we are having a vector of a, b, and you are asked to normalize it. What you're simply going to do, you're going to be multiplying it by 1 over the square root of a square plus b square. This is just how to normalize a vector. So it's more like the magnitude formula in vectors. You just divide, you just doing the inverse of it, or kind of reciprocal of it, 1 over that magnitude formula. So if it is something like this, it's also going to be 1 over what? So the idea is for each element. So even though it's a 2 by 2 or a 3 by 3 matrix, each element you're going to be doing this. So let's say that if this turns out to be C, D, what it means is that our square root system will still continue. So we have a square plus b square plus c square plus d square, all in square roots. This is how you normalize the what? The vector. Now let's do that for this. When we do that for that, we're going to be having that our x1 is equal to 1 over square root of 1 square plus 1 square. Everything, I'm sorry, multiply by what? Matrix of 1, 1. Now 1 square plus 1 square is 1. 1 plus 1 is 2. So we can have that our x1 is equal to 1 over root 2, 1, 1. So this is your answer for the first eigenvalue. we're going to be repeating the same thing now for the second one too. For the second one. Okay. Now, so we can just say that our eigenvector for our eigenvalue of 5 is now going to be 1 over root 2, 1, 1. That's now for us to find for what? X2. So, doing that, we have that our, using the same formula, we have our 3, 2, 3, sorry, 2, 3. Now, all this is multiplied by your what? X and what? Y, which is equal to your lambda multiplied by your X and what? Y. Here, our lambda is what? 1. So, we're going to be having 3, 2, 2, 3. 1 multiplying anything will still remain that thing now. So, when we solve this into this, we have 1 times all of that, which still remains what? That nothing changes. So now from here, we can now bring it back to its normal equation form. So we have 3 times x, we have 3x plus 2 times y is equal to what? Your x. This times this plus this times this is equal to this. And 2x plus 3y is equal to what? Y. Now, we have gotten our equation. Now we're going to simplify. Remember, the aim is to express one term in term of the other. So keep y one side, keep x one side. When you do that, you'll be having that 2y, this guy coming over here, to then become is equal to minus 2x. Am I wrong? Am I wrong? No, I'm not. So when this crosses over, it becomes what? Minus 3. We're having 1 minus 3, which is what? Minus 2. When this crosses over, you have x minus 3x, which gives us this. Now, over to the next one. Okay, to also further simplify this one, we can then say that this is equal to, from here, that y is equal to what? Minus x from this first one. Let's bring this one down. So we're having 2x plus 3y is equal to what? Y. Now from here, the same thing, expressing one term in terms of the other. So when we take our y over, we're going to be having 2x is equal to minus what? 2y. This will then tell us that our x is equal to what? Minus y. Now our eigenvector is now going to be for our x and y. Now I want to use x, so this is now going to be x, still representing x, but our y is equal to what? Minus x. So here will then become what? Minus x. If I wanted to use y to represent the two of them, here will be y, while up here will then become what? Minus y. So we can also write this to be, just when we multiply it by our 1, we then have 1 and what? Minus 1. Now we also need to normalize it. When we do that, we then have that 1 over root 1 square plus minus 1 square, all multiplied by your 1 minus 1. Now when you solve for that, you then have that your answer is what? For your x2, you have that 1 over root, this is 1 square is 1, minus 1 square is so what? 1. So 1 plus 1 is what? 2. Multiplied by your matrix 1 minus 1. So here is going to be 1 over root 2, 1 minus 1. So we have succeeded in getting the eigenvalues and what? Eigenvectors. Remember that your eigenvectors, they don't have any linear relationship. That means there is no way you can plus or there's no way you can manipulate this one by plussing or multiplying anything for you to get this one. The only relation they have is with their what? Their eigenvalue. The eigenvalue will give its own separate eigenvector, and the but the eigenvector have nothing in common, like no relationship that we will be able to derive the other. So it's not like as if you know x1, you can use another formula to get this one without stressing yourself by going back to this one. So each eigenvector is derived by its what? Eigenvalue. So you cannot use an eigenvector to derive an eigenvector. Another thing again that you also need to know is that for a diagonal matrix, is eigenvectors. Let us say if you're told to find the eigenvalue and eigenvector of 3, 0, 0, 2. Your eigenvalue here is going to be 3 and 2. So for your a diagonal matrix, your major elements, or the element in the major diagonal are actually your what? Your eigenvalues. You can use this now to then get to your eigenvectors. So this is one rule you need to know. So if you know this, you don't start going through the whole process of using this formula to derive your eigen values. So long as diagonal, just this is your first one, this is your second one. This also goes for your 3 by 3 or 4 by 4, any as long as diagonal. The number of your diagonal, the major diagonal elements are the number of your what? Are the values of your eigenvalue. And that thing is that your eigenvalue will have the same number as the number of rows and columns. If you notice of your A, if you notice your A is 2 by 2, so definitely your eigenvalue will be 2. If it's a 3 by 3, your eigenvalue will be 3. If it's a 4 by 4, your eigenvalues will be what? 4. And 4 eigenvalues means 4 what? Eigenvectors. So okay. Now, and one more, and another thing is this. It's also good that you also know that when you sum up all your eigenvalue, when you sum up all your eigenvalue, the sum of all your eigenvalue, in this case, y1 plus y2 is equal to the sum of the major diagonal value of this. So in this case, is what? 3 plus what? 3. Here is what? 5 plus 1. 3 plus 3. This will definitely give us what? 6. This also give us what? 6. So when the addition of these two is equal to the addition of your major diagonal what? Elements. Now the product of these two is also equal to the determinant of your A. The determinant of your A. So in this case, we have that our determinant here, in that case, so the product of this, we're going to be having again 1 times again 2 is equal to the determinant of what? A. Remember what this one was telling us? We call this one the trace of A. When you add up the values of your major diagonal, we call it the trace of that matrix. So when you add up these two values, this also goes for your 3 by 3, 4 by 4, 5 by 5. It doesn't stop only in 2 by 2. So long you are, so this can come in form of equation. So it's good that you know it. These are the properties of your eigenvalues and eigenvector. Now when you multiply these two, it will definitely give you the determinant of what? Your eigenvector. Now let's confirm this. When we multiply these two, we're going to be having 5 times 1, which is definitely going to give us what? 5. Now over here, our determinant of that guy is going to be 3 times 3 minus 2 times 2, which is equal to what? 9 minus what? 4. And 9 minus 4 is what? 5. So it's good that you know these properties. So that's all for this video. Subscribe if you haven't. Like, share, comment, and live a wonderful life. God bless you guys. See you guys in the next video. Goodbye.